Hi everybody. Today my topic is beam element stiffness matrices. To get a beam element stiffness matrices, we need to make relationship between the force and the displacement. To get in details of it, let's move ahead. On a beam, if we apply loads, then beam suffers displacement and rotations. These fundamental characteristics governs the behavior of elastic structure. That's why we need the relationship between the applied loads and the displacements. And this relationship we can write as this one. The stiffness matrix for a member is used to express the forces at the ends of the member as a function of the displacement of the member ends. It's very important points. Here F is a vector representing the forces acting on the elements at its nodes. That's why this one we call element and force vector. K, it is the element stiffness matrix. It is related to the degrees of freedom at the nodes relative to the local coordinate system. This is also important point. D is the element displacement vector. This displacement, it is actually for translational and for rotational. And here I will develop element stiffness matrix related to an element local coordinate system. And in addition, I want to mention here that I am not going to do structural stiffness matrix, so I will not discuss anything about global coordinate systems. So my discussion will be limited in local coordinate system. Let's move ahead. Here, considering an element with only 1 degree of freedom. Here in figure I showed the axial stiffness of a column. It is axially loaded column. For this reason, here the matrix and the vectors can be written as like this one. Here we can see the force necessary to maintain a unit displacement. This is the definition of stiffness. The force necessary to maintain a unit displacement. This is the definition of stiffness. So the equation, this one, I mean matrix and vector relations. Here EA, it is the axial stiffness for a structural member that mainly resist axial load. Here we can see the axial load F. in this column, and same behavior we can see in the truss member also. So this is 1 degree of freedom. This one, it is force vector, this one displacement vector, this one stiffness matrix. Here displacement, if we take as 1, so this will be the stiffness. Here we consider a beam element of length L and Young's modulus E, cross sectional area is A, and this beam element is subjected to axial forces F1 and F2 at the end A and B. So we call this node A, and this end we call node B. If we assume that node A, it is displaced del 1 in the direction of the longitudinal axis, I mean x direction. Already I showed here x direction and y direction. So if it is on x direction, and similarly this node B is displaced a distance del 2 in the same direction. So these two quantities, I mean here we assume that del 1 greater than del 2, and these two equations, I mean one is F1 and another will be in terms of F2. There is two equations here. We can write it as like this, and here the K, it is 2 degrees of freedom. 2 degrees of freedom, because once we put this stiffness, because for this equation this term AE over L, this AE over L, this term and this term, this is the element of stiffness matrix. And also here we considered that F2 equal to minus F1. So here we got F1, this is stiffness, and this one is the displacement, and by simplification we can put like this, del 1 del 2 separate, and here also del 1 del 2 separate. The reason, I will write it as a matrix. So this is that matrix. So this is force vector, this is the stiffness matrix, and this is displacement vector. And 2 degrees of freedom, that is why 2 by 2 matrix. Here I have taken a beam element, it is with flexural rigidity EI. In other way I can say EI, it is bending stiffness for structural member, and it mainly resists bending stresses. Bending stresses, it is moment in a beam, and here this beam length is L. Now this uniform beam has two ends. This is one end, this is other ends, and I marked it as node 1 and node 2. At these nodes where forces are applied, we can see here forces are applied and displacement are measured, because when we will do the calculations, so forces are applied, displacement are measured. The thing is like this F1 and F2 are the nodal forces. So we can say that beam is subjected to nodal forces. This is actually transverse shear F1 and F2, as well nodal moments, I mean bending moments. Which one? M1 and M2 at both ends. At the beginning I told, due to these forces, beam suffers nodal displacement and rotation, and it is most important to consider it properly. So where is displacement? Displacement is this one, nu1 and nu2. Where is rotations? Rotation is this theta1, this theta2. And here in previous two slides I discussed about axial loading, but here I did not include any axial forces because my target is to use 4 degrees of freedom. So 4 degrees of freedom means I will have 4 by 4 matrix, stiffness matrix. That's what you can see here, 4 by 4 stiffness matrix. This stiffness matrix, this I can call it as a K. It relates the shear forces, this F1, F2, shear force, M1, M2, bending moments. So this force vector, it relates to this one, deflections and rotations. This nu1, nu2 are the deflections and theta1, theta2 are the rotation. So what I can say, this beam element stiffness matrix K, it relates shear forces and bending moments at the ends of the beam to the deflection and rotation at the end of the beam. So it makes relations by this matrix. Here actually if you look at this x-axis, it is taken parallel to the axis of the member, and positive sense is designated. A positive y-axis, it is perpendicular to this x-axis. Positive sense of rotations. We did it by using standard right hand rule. This positive sense. Now I shall derive stiffness matrix for a uniform beam, because here it is written K11, K22, K13 like this. So what I will do, in first slide I will discuss about the first column, how to get the first column. Then I will see how to get the second column, then third column, then fourth column. I shall find in next slides. Let's move ahead. The relations, if we look at this, the relations between the joint forces and the joint displacement are developed by assigning an arbitrary value to a single displacement component, while requiring all other displacement components to remain equal to 0. Here I have to get the first column of the stiffness matrix. As I told already, I need to get the first column of the stiffness matrix. In previous slide I showed the matrix, 4 by 4 matrix. So in case of getting the first column of that matrix, I have to set forces and moments corresponding to the following set of displacement and rotations. So what I will do, new 1, I will put 1, all other will be 0. And this is the resulting deformed beam. Here node 2 is fixed. If node 1 of the member is displaced relative to this node 2, so chord of the member rotates anti-clockwise. You can see that. So the moment can be related to the displacement, this new 1. I put here 1. This new 1 value is equal to 1, assume. That's why the moment, it will be related to the displacement of this new 1, this moment. And we can check it by using conjugate beam methods. Then we get F1, M1, F2 and M2. So what I got M1 I got this 6EI L square new 1, and M2 I got 6EI L square new 1. So I got these two moments. Now adding these two moments, M1 plus M2 divided by L, I get this F1. And F1 and F2 will be in opposite signs, so this is plus, this is minus. And these values are these 4 values are the first column of the stiffness matrix. This one, this part. This will go for the displacement vector, this new one, but this part, 12 EIL cube, 6 EIL square, these and this. It's the value of like this one for K11, this is K21, this is for K31, this is for K41, first column. Here to get the second column of the stiffness matrix, so we have to set the forces and moments corresponding to this following displacement and the rotation. So what is that? This rotation is 1, all other is 0. Here node 2 is fixed. If node 1 of the member is rotated by this theta 1 relative to the node 2, then chord of the member rotates anti-clockwise, and moment, of course, it will be related to this theta 1. So what is the value? Value will be like this, F1, then we get M1, then we get F2, then we get M2. So here if we look, we can see that M1 we got 4 EI over L here, but here it will be half, so 2 EI over L. Now adding these two, M1 plus M2 divided by L, we get this F1. And same way this plus this divided by L, we get F2. Now here we got the second column of stiffness matrix K. This, these and this. This one is K12. This one K22. This one K32. Yes, K32. This one K42, because second column and last row, so K42. So this total, this line is the second column of our targeted stiffness matrix. Third column of the stiffness matrix, it is set of forces and moments corresponding to the following displacement and rotations. Here this new 2 will take 1 and all other will be 0, and this is the resulting deformed beam. Here node 1 is fixed. If the node 2 of the member displaced relative to node 1, so that the chord of the member rotates anti-clockwise, and from arguments of symmetry of the element stiffness matrix we know, then we find M1 or M2 equal to, here we can see that this one, M1 and M2. M1 equal to minus 6 Ci over L square nu 2 and M2 equal to minus 6 Ci over L square nu 2. This is the moment due to this. Due to this nu 2 equal to 1. Now adding these two and divided by L, M1 plus M2 divided by L, we get this F1 and this one F2. Here negative, here positive. So this is our third column. This is our third column of the stiffness matrix. Third column means it is 1 3 K13 K23 K23. This one will be K33. This one will be K43. Yes, K43. It is third column of the stiffness matrix. The fourth column of the stiffness matrix, it is set of forces and moments corresponding to this set of displacement and rotations. Here last things, theta 2 considered 1, others are 0. So here node 1 is fixed. If node 2 of the member, it is rotated by theta 2 relative to node 1, so that chord of the member rotates anticlockwise. So moments, it is related to theta 2. So what will be our value for F1, M1, F2, M2? Previous slide our M1 was 4 EI and M2 was 2 EI. In the second slides, in the second column, in the second column of the stiffness matrix. But here our M1 is 2 EI over L and M2 is here. Previous in the second column stage, when we discussed, then 4 EI over L was here because that time 2 was fixed end, but now 1 is fixed end. So our M1 will be 2 EI over L and M2 will be 4 EI over L. Adding these two, M1 plus M2 divided by L, we get this F1 and F2. This one positive, this will be negative. So these four are the fourth column of the matrix. Stiffness matrix, this is fourth column. This is K14, K24, K34, K44. This last 4 slides, we can write it as a 4 equations, like F1 equal to, we are taking these 4 items from last 4 slides. Then we can write equation as M1, then again F2, again F4. So it means it gives us 16 terms of beam element stiffness matrix, 16 terms, because here 4, here 4, here 4, then here 4. Now all this term we will use in stiffness matrix. So we remember that we got 16 terms of beam element stiffness matrix. So this is that matrix. Just only the things I put EI out of this matrix. It was inside, so it is taken out. So this is the matrix, whole things. This is the displacement vector. This one force vector. So force vector, displacement vector. And these two vectors are related by this stiffness matrix. It has 16 elements. So as I told, this is force vector, this one is stiffness matrix, and this one is displacement vector. So we got it, beam element stiffness matrix. So we got the stiffness matrix. In common way, we can write Kij in generalized form. Here I wrote that 4 by 4 matrix as Kij in generalized form, where Kij is the stiffness matrix of the beam. Now here I want to put an additional informations. We can transform this matrix to an structural matrix. How? Using transformation matrix by this equation. We can do this. If we want to convert our local coordinate system matrix, I mean beam element stiffness matrix, because global coordinate system, if we want to get, I mean structural matrix, then we have to apply transformation matrix. Using this equation we can do that. TT, it is transpose of T. And that's all for today. Thanks for watching.